we're going to focus on growth and decay as well as compound interest. We're going to start by talking about population growth. Its function, P of t, is equal to P sub 0, where it is the population at 0 time, e to the power of kt, where k is the exponential growth rate, so how fast we're growing, and t is after how many years, or time in which it's growing. So let's look at, in 2014, the population of Ghana, which is located on the west coast of Africa, was about 25.8 million, and the exponential growth rate was 2.19% per year. Using this information, let's find the exponential growth function. So the population with which we're starting at this particular time is at 25.8. So 25.8 is our P sub 0. Our growth rate, so our K value, is 2.19% and then per year, where T would then be the number of years since 2014. Our K value we always write in a decimal form, so 25.8 times e to the power of 0.0219 times t, and this is in our exponent, where t has to be the number of years since 2014. Since 2014 is when this population we were talking about. We are able to graph the growth function by looking at Desmos. So I graphed the function y is equal to 25.8 e to the power of 0.0219 and then x in this particular instance. And then we're able to do a couple things. We're able to estimate the population in 2018. Well, 2018 is 4 years after 2014, so we're going to evaluate this function at 4. When we do that, we get approximately 28.2 million. Another way we could do that is using the intersect method using Desmos, where on one line I have what is x equals 4, and where does it intersect my function that we had classified earlier. Y is equal to 25.8 e to the 0.0219x. And where do they intersect? At 4 years, they intersect at a population value of about 28.2 million. At this growth rate, when will the population be 40 million? So now we're looking for how long will it take the population to reach 40 million. So I know that my population now is 40, and then we can solve for our value of t since we're looking for time. We can go ahead and get e by itself so that we can use the natural log. So we'll divide both sides by 25.8. Then I'll take both sides to the natural log, since I know the natural log and e will end up canceling themselves out, so that the natural log of this number here is equal to 0.0219t. And then to get t by itself, we'll divide both sides by 0.0219 so that t is by itself. Using our calculator, using our calculator, we can simply type that value in, since the natural log of a number is just a number itself, and we'll see that it's about 20. So about 20 years after 2014. So in the year about 2034, we could expect the population to reach about 40 million. We could also use the intersect method as well. The intersect method here we replaced our y value with 40, and then the red line is our function itself. Compounding interest continuously. When an amount P of 0, so our original amount, is invested in a savings account at an interest rate R, compounded continuously, The amount with which we earn in the account after t amount of years is given by this function. Notice how similar it is to the growth rate function. It's identical. Suppose that $2,000 is invested at an interest rate K, compounded continuously, and grows to $2,504.65 in 5 years. Let's identify the interest rate. Okay, so I know that the amount that we're starting with, P of 0, we know that the amount of years, so our T is 5, but we don't know what K is. We need to identify what is our K value. We do know that the amount that we've earned after all that time is $2,504.65. That's equal to 2,000 times e to the power of K times 5. Let's start by getting e by itself so that we can use the natural logs to evaluate. We'll divide both sides by 2,000. Then we can take the natural log of both sides. And when we take the natural log, we know the natural log and e cancel one another. So I'm left with 5k. And then take the natural log of all those values divided by 5, which gives us a value of 0.045, which is k, and its interest rate, then turning that decimal into a percent, is about 4.5%. We could also use the intersect method. Notice that our horizontal line here is y equals $2,504.65, and this dark line, this grayish dark gray line, is our 2,000, y is equal to 2,000 e to the power of 5x. So where they collide with each other is at about 0.045 or 4.5%. Continuing more information on this to answer more questions, it's asking us to find the exponential growth of the function. Well, now that we know the rate at which we're growing, we can find more information because we know the general formula is going to be 2,000 e to the power of 0.045 times t. Now that we know the general form, we can actually find the balance after 10 years because our 10 is going to be our new value of t. Evaluating at 2,000 times e to 0.45, we see that the balance will be approximately $3,136.62. Notice that I replaced x is equal to 10 for my blue line, and then my dark gray line is our original function, and I found their point of intersection. So 10 represents the number of years, and our y value represents how much money we will have. Similarly, after how long will the $2,000 have doubled? Well, if we're looking for how long after it has doubled, double our money would then be $4,000. So we want to know how long it will take to earn $4,000 in this account. So I have y is equal to 4,000 and then our function on the right-hand side where we now can solve by dividing both sides by 2,000. So 2 is equal to e to the power of 0.045t. Taking the natural log of both sides so that my natural log and e will cancel. And then dividing by 0.045, we say it'll take about 15.4 years to double. Also using the intersect method, we had replaced y with 4,000. And then our dark gray line is still our original functions that we could identify where they cross each other. What we just found is known as the growth rate and doubling time, the time at which it takes something to double how much we have. So k times t, the doubling time, k is our growth rate, t is the doubling time. We have these three equivalent formulas. So it's equal to the natural log of 2. Or the growth rate is equal to the natural log of 2 divided by the doubling time, or the doubling time is equal to the natural log of 2 divided by k. As long as you know one of these formulas, it is very easy to get all of the rest of them. So it says that the population of the Philippines is now doubling every 37.7 years. What is the exponential growth rate? So we're looking for the growth rate, but I do know the doubling time. The doubling time is 37.7 years. So when I substitute this into the formula, I'll take the natural log of 2 divided by 37.7, and we get approximately 0.0184. or about 1.84%. This tells me then that the growth rate of the population in the Philippines is about 1.84% per year. A lake is stocked with 400 fish of a new variety. The size of the lake, the availability of food, and the number of fish restrict the growth of that type of fish in the lake to a limiting value of 2,500. The population gets closer and closer to this limiting value, but will never actually reach it. The population in the fish in the lake after time t in months is given by this function. We have 2,500 over 1 plus 5.25 e to this value of negative 0.32 times t. This 2,500 is our limiting value. Things like food, space, and resources are limiting the amount of fish that we'll have. It's also acting as a horizontal asymptote because we'll never have more than 2,500 fish in this lake due to the limitations that this lake has. So I'm going to use Desmos to graph it, and now we have the graphing picture. And now we can find the population, since P of t represents the population after these amount of years. By using the table tool in Desmos, we can easily find these values, such as P of 0, we would have 400, P of 1 is 519.5, P of 5 after 5 months we'll have 1,213.6, after 10 months we'll have 2,059.3, 15 months we'll have 2,396.5, and after 20 months we'll have 2,478.4. If we continue the number of months to increase, we will get closer and closer to 2,500. However, we will never actually reach that 2,500 limit, since it is a horizontal asymptote. We can also look at decay. Exponential decay. Notice that this formula is the exact same as the one previous for exponential growth, except it's a negative in our decay rate versus a positive. We also can find the decay rate or half-life. And notice that it's the exact same formula as the double life. Notice we have what is half-life. It is the amount of time it takes for half of the atoms in a sample of a radioactive substance to decay. And it can be useful in a couple of upcoming examples. So let's say we have the following 4 radioactive substances. We can find the decay rate and or half-life given one or the other. So I'm looking at polonium. Its half-life is 3.1 minutes. So it takes 3.1 minutes to have half of the atoms to decay. Okay, so we can find the rate. K is equal to the natural log of 2 divided by the time it takes. So the natural log of 2 divided by 3.1 would give us about 22.4% per minute. So polonium decreases at a rate of 22.4% per minute. Let's look at lead. How long does lead take to get its half-life? It says 22.3 years. So if we take the natural log of 2 and divide it by 22.3, this is decaying much slower, as it decays 3.1% per year. Let's go backwards. Let's find the half-life. So let's solve for T. T is equal to the natural log of 2 divided by the rate at which it's decaying. So let's look at iodine. Iodine, we're going to take the natural log of 2 and divide it by its percent, which we turn to a decimal, 0.0115, is about 60.3. Here it's per day, so days. So it takes 60.3 days for iodine for its half-life. And krypton. Krypton decays at a rate of 6.5% per day. So if I take the natural log of 2 divided by 0.065, we get approximately 10.7 here. We're days to get its half-life. Example 6, the radioactive element carbon-14 tells us that its half-life is 5,750 years. The percentage of carbon-14 present in the remains of organic matter can be used to determine the age of that organic matter. Archaeologists discovered that the linen wrapping from one of the Dead Sea Scrolls has lost 22.3% of its carbon-14 at the time it was found. Let's determine how old the linen wrapping is. We know we're going to use the decay rate here, but we don't know. We need to find the rate of decay. How fast is it decaying? We know that 22.3% has lost, but we need what is currently present in order to complete this. We'll come back to that in a second. We know that the time it takes to reduce its half-life is 5,750 years. So we can find K by taking the natural log of 2, dividing it by its half-life. And we get a super teeny tiny number. Use this anytime, use this K value anytime in your homework where it's asking for the half-life of carbon-14 rather than retrying to find it. All right, P of T is equal then how much we originally had to the decay rate of 0.0012 times T. Well, we don't know what we originally had, but we can find currently present. The amount that's currently present, I should say. If we started with 100% and we subtract how much it's lost, we know then it currently had 77.7%. Turning that into a decimal then, we'll have 0.777 times the original amount that we had, which we're unsure about, is equal to the original amount E times 0.0012T. What's great then at this point is that we don't need to know the original amount. We can divide both sides by P sub 0 and they'll end up canceling out. I then can take the natural log of 0.777 equal to the natural log of E so that I can get rid of the exponent and bring that exponent down since these will end up canceling. The natural log of 0.777 will just be a value. And when I divide by negative 0.0012, I see that time is about 2,103 years old. Similarly, let's look at another example. In February 2006, in the Valley of the Kings in Egypt, a team of archaeologists uncovered the first tomb since King Tut was found in 1922. The tomb contained 5 wooden sarcophagi that contained mummies. The archaeologists believe that the mummies are from the 18th dynasty. The 18th dynasty is between about 3,300 to 3,500 years ago. Determine the amount of carbon-14 that they would have lost in this year range. We do know the carbon-14's decay rate, but we don't know how much is remaining. We don't know how much is remaining. We do know that we have P of t is equal to P sub 0 e to negative 0.00012 t. Since we're dealing with carbon-14, we can reuse that decay rate. We don't know what actually remains. We don't know what remains, so we don't know how much we originally started with. However, we do believe that the time is originally 3,300 to here. So we're going to split this up and do what remains between 3,300 and 3,500. Just like the last example, the original amount can cancel because we can divide both sides by P sub 0. This then gives me x is equal to e to negative 0.0012 times 3,300. Since that's all a value, we can plug and chug into our calculator and we obtain 0.673. This tells me that about 67.3% is remaining. We're interested in how much is lost. So this tells us how much is remaining. We want to know how much is lost. So to find how much is lost, we will take 100% minus 67.3%, and we see that it would have lost about 32.7% 3,300 years ago. We also need to do the same then for x equal to e to the negative 0.0012 for the high end of 3,500. When I substitute that in, we obtain approximately 0.657 or 65.7%. Again, that's how much is remaining. To find how much is lost, we'll take 100 minus that 65.7% and obtain 34.3%. So our ending result then, to answer the question, is that the amount of carbon-14 that the mummies would have lost during this time frame, it would have been between 32.7% to 34.3%. And this concludes our lesson utilizing models of growth and decay as well as continuous